Okay, let me do this again. He's Professor Chih-Ting, and he's from Nanjing Normal University, and he will talk about hadronic uncertainties versus new physics for the W boson mass and muon G-2 anomalies. Please start when you're ready.
Okay, so first of all, thank you for the introduction. And I would like to thank Professor Ko to give me this chance to visit KIOS and give a report. And today I will give this title, the hadronic uncertainty versus new physics for W boson mass and the muon G-2 anomaly. So maybe most of you already know this too. The W boson mass essays from the CDF 2 will be reported about 2 years before, and the muon G-2 anomalies also reported by the last years. The Fermi lab announced, combined with the data, there's more than 5 sigma apart from the standard model prediction, but that have some assumption. They use the data-driven for this hadronic contributions. So in this talk, I will base on these 2 papers. The first one is a Nature Communication paper, and the second one is a PRD papers. And my collaborators, most of them are from the NNU BSN group. Professor Peter Oslo, Professor Andrew Foley, Professor Lei Wu, Professor Yongchen Wu, and Bin Zhu from the Yantai University. So in this talk, I will separate mainly to the 3 parts. The first one, I will show you an introduction and the era of standard model precision measurements. And actually, we are very lucky. We are in this era of precision measurement. So now we have more and more precise to measure the standard model prediction parameters. And the second part is the main part of this talk. I will show you our electroweak fits of the W boson and the muon G-2. And the third part is we found from the second part, we realized the hadronic uncertainty, as I mentioned in my titles, it cannot simultaneously explain this W boson mass and the muon G-2 anomalies. So that means we need a new physics to explain both of them together. And in this work, we use the scalar leptoquark models. And finally, I will give a conclusion. So let's start from the first part of the introduction for the standard model precision measurements. So I think now is the era of standard model precision measurement in Collider experiment. And one of famous this kind of precision measurement is for the Higgs mass predictions. So as we know, before we found the Higgs boson RLC, actually we can already use the standard model precision measurement to predict its mass. And as you can see, for example, in this red dashed line and blue dashed line, at that time, it already predicts the Higgs boson is about 120 GeV, even we don't find out. So you can see that's so powerful for this kind of electroweak precision measurement. So that is one example, so that we need to care about the electroweak precision measurement. So let's go back to see our standard models. We all know it's a SU3 cross SU2 cross U1, and after spontaneous symmetry breaking to SU3 color cross U1 electromagnetic field. And this model, the model is very beautiful model because there are only 19 free parameters. And if we take closely, and 9 of them are from the fermion mass, they are free parameters. And 4 of them from the secant matrix, 3 angles plus 1 CP base, and also 3 gauge couplings, and 1 QCD BQ angles, 1 theta QCD. And until now, we still don't know why these are so small, close to 0. So that's a so-called strong CP problems. And the final 2 are the Higgs BQ spatial values and the Higgs mass. So let's see one by one. The first is about the fermion's mass. So after the Higgs boson already been discovered, we can have more and more precise measurement of their Yukawa coupling and test the Higgs mechanisms. So you can see the left-hand side is Atlas result and the right-hand side is CMS result. Here the dashed line is the cinema predictions, and you find almost all points are in these lines. And now we move down to the second generation of fermions. Now the muons also in a good agreement of the cinema prediction. Then we turn to the Chang quarks. So more or less, now the cinema prediction for the Yukawa coupling and the Higgs mechanism are in a good test from the LSD's problems. So this is the first part. We test for this mass, fermion mass in the standard models. And among them, the top quark mass is most important when we do the electroweak precision measurement fittings. And here is the combination of the Atlas and CMS for the energy of 7 and 8 in the round 1 data. And after the combination, they found the direct detection for this top quark mass is about 172.5 GeV. And this is the most precise value what we have now and also appear in the PDG. So keep going for the 13 TeV data. We found on the left-hand side, the CMS, their measurement of the top quark mass are more or less consistent with their round 1 combinations. You can compare with this red shadow line. However, for the Atlas case, you find for their soft muon tag, their prediction mass is a little bit larger than their Atlas round 1 combination, and we still don't know the reason why they have this larger value of top quark mass. But however, for their round 2 dilepton measurements, more or less considered consistent with their round 1 data. And I will show you later why we have the heavier top quark mass will have some effect when we consider the W boson mass, because you will know later all of these parameters, Higgs mass, the top quark mass, and W boson mass will all play roles in the electroweak fittings. Another part is about the secant matrix. So now we have more and more precise measurement of this secant matrix, but we still have this so-called secant matrix anomaly. So what is this anomaly? If you take a close look of the first line and the first row of the secant matrix, you find although this value, the 0.9985, is very close to the 1, but however, because they will have a very small uncertainty, it's about 3 sigma apart from the 1. So this is so-called secant matrix anomaly in the first row. And if you also see the first column, you will also find the value is 0.9970, and the uncertainty is even larger than 18%. However, this value is a little bit smaller than 1. So the reason why this is not consistent with 1 is still the problem. So some people, they use some BSM models to fit, so such that this value can more close to the standard prediction. But we still don't know if this is some uncertainties for our measurement or there's some new physics insight. So this is one issue.
That's the usual Cabibbo angle anomaly?
Yes.
The first one?
Yes, this is a Cabibbo anomaly. Many come from the first one. Yes.
It's about 3 sigma.
Yes, about 3 sigma. Until now, still about 3 sigma. Okay, so this is one, the first puzzle. We are not sure in the cinema parameters why they have this inconsistency. And the other part is about the gauge couplings, for example, alpha 1 and alpha 2. And so for these parameters, we can use the alpha EM in the Z pole and this psi theta W. And here the psi theta W means the sign of the Weinberg angle or weak missing angle on Z pole. And right side from our PDG data, you find our previous client measurement have a good agreement in this RGE roundings lines. And here, these are alpha EM values, very precise measurements. And now we also have the CMS certainty, the primary data, and this red point. It's also consistent with the cinema predictions. So now we have a very precise measurement of this psi theta values and also these alpha EM values. So that means we have a good precision, agreement with the alpha 1 and alpha 2 in the cinema prediction theoretical experimental. And the other one is for the strong coupling constant alpha x, also on a Z-port. And in the left-hand side, we have several ways from the low energy experiment and also the lattice QCD results. And finally, combine of them, the PDG results about 0.1179 values. And as you can see, the uncertainty here is also very small, about for 4 digitals. And currently, last year's Atlas also reported new results. And for their ATD measurements, the central value is about 0.1183, but they have the same small uncertainty as their combined one. So this is a good achievement. Now, from the collider experiment, we can have such small uncertainty when we measure the strong coupling constant. And then the other one is about the Higgs boson mass. So we also combine the round one data for the Atlas and both of them are Atlas. Yeah, both of them are Atlas. And you find after combining round one and round two of the Higgs to diphoton and Higgs to photonleptons, the final Higgs boson mass is about 125 GeV. And in the futures, we can have more and more precise measurement of this mass other than C. Then all of them are the parameters as I show you in the right-hand side. So when I do the electroweak precision measurement, we will not directly use the parameter I used at that time. Because of the measurement issues, sometimes we will change some parameter for some is more easier to be measured. For example, we will use the Z boson mass because these values we can have a more precise measurement, especially in the E plus E minus collider. And as you can see, for the previous measurement of the Z boson mass is in a good agreement of the cinema prediction. And for the different kind of experiment, the agreement in this black line. And also for the width of the Z bosons, they also have the lepton flavor universality for the mu electron and the tau. So they have the values very close to the one. So now for the Z boson, we have a good agreement for this mass and its width. And we also have a much smaller uncertainty compared with the W boson measurement. So the Z boson, its mass and width is important when we do the electroweak precision measurement. And the other set is for the W boson mass and its width. Previously, people not so care about that. Just 2 years before the measurement of the CDF 2, they found one very strange thing. Their result is report here, the blue line. They used the 2002 to the 2011 data about 8.8 femtobarn inverse. They find their values of A0434 plus minus 9, and compare this value with the standard predictions. The blue line, although they look like very close to each other, but however, because their uncertainty are very small, so they're about 7 sigma deviation between these two. So at that time, people are take this seriously. Maybe this is a hint of new physics. But if you don't see this one and compare with other value, you will find more or less the data is consistent with the standard prediction. For example, the LACB, this value, the central value is directly at the standard prediction. The red line, the red dash line, the green dash line is for the standard prediction, SA. And for the Atlas one, this is the prediction also very close to this green dash line. So this should be a very surprising result. People don't know why these are far from the standard model predictions, and large about 7 sigma deviation. So at that time, that was big news, and their paper published in the Science. This is one point. Another point, this is the first time experimentally they have the uncertainty just older MEV scales. You can see for the previous data, they have very large uncertainty. And we can only have the order 1 MEV uncertainty when we combine the data. But now for the single data set, we can have order 1 MEV scale. So that's two important things why the paper can be published in Science. But unfortunately, in the data sets, there's no information for the measurement of the W boson width. So compared with the previous world average, these values is consistent with the standard model prediction. So at that time, I have attended one workshop, and Professor Tauhan, he told, he not so believe this CDF result. The reason is because he think if we have the axis here, then there should be also an axis from the W boson mass width, because they have correlated to each other. But for the CDF result, they don't report this one. So he said he will believe this result will be true in the future. They also report this W boson width measurement. But unfortunately, the CDF2 result, they don't report this width measurements. So when this result appears, so we ask our question, so how does the W max from the CDF2 affect other precision observable? Because as you know, if we change the mass of W boson and putting the electroweak fit, then other parameters for the standard model will also change. So that will get everything much different than the prediction we had before.
So here simple combination, does it include the CDF new result or not?
This simple combination will combine the lab, LCB, Atlas, and also CDF.
All the CDF, all the CDF.
Tabletron 5, combine 5 data set.
And
But
where is the new CDF result?
Here.
That's the new result.
New result. But there's one assumption, because we don't know their correlations. So this is very simple combined without a correlation to each other. Because the correlation only experimental people will know. So this is just the naive combinations. So if we involve the correlation between those data, then they also change this combination. As we know, they will move this one a little bit close to the standard model prediction.
So this simple combination includes the CDF new result.
Yes, but no correlation among these data.
And all the result, all of them.
Yes.
So it's a little bit smaller than the new CDF result itself.
Yes, and we have checked for the CDF1, if you only have this single data, it's about 7 sigma deviation. Then for the combined one, it's about 6 sigma deviation.
So are there any attempts to combine this with the correct correlation or not?
The reason is because we don't know.
No.
And experimental people say they will combine, but until now, there's no result. Yeah, so right, that's the issue. Okay, so just in these years, in March, and the Atlas also reanalysis their 7 TeV results. But however, they find for their Atlas 2024 data, within 1 sigma region is more or less consistent with this block line. This block line is a standard model prediction. So in their result, they announced there's no axis of this W boson mass. And you can also see in the right-hand side figures, as I showed you before, the W boson mass, top quark mass, and Higgs should be correlated to each other. And therefore, they will, in the 1 sigma and 2 sigma region, they are all consistent with each other. So for the Atlas group, this is good, consistent, good consistent with the sigma prediction. So there should be no this kind of passes, but we don't know because their uncertainty is quite large, 16 MeV.
Sorry, I have a very naive question. In this plot, the D0 result and CDF result looks quite different, but these two experiment groups are focusing on the Tevatron, the same Tevatron experiment, right?
Sorry, you say
The D0 and CDF experiment group.
yes,
Yeah, in this
there are
case,
two
yeah.
groups.
Would you please tell me whether you have any reason why D0 encompassing the blank line and why the Tevatron, I don't know, why CDF cannot encompass the blank line?
Yeah, that's a good question. But as you can see in the previous D0 and CDF results,
Yeah,
previous symbol, this one is a little bit weird, but
yeah, very
some
weird.
some of them are more or less consistent. D0 at least D0 and right. CDF a little bit larger than the D0 prediction, but I don't know reasons. Yes, there's the previous measurements.
Yeah, if the D0 and CDF measurements are consistent, then we can say there is more powerfully there is a new physics, right? Because these two experiment group consider the same experiment Tevatron, right?
Right.
Yeah, but the difference between the two measurements looks very weird.
Yeah, one reason for that because you can see the luminosity. For example, for this one, they have a very small luminosity.
Yeah, yeah.
Compared with this 4.3 megabyte per second, 2.5%. So there may be some reasons because of this less data point, so making it so large. So that's maybe one reason. Yeah. So, and this is one result. Another one is for the Atlas, they also try to measure the W boson width. Yes, please.
Gyaro, do you hear me? I think yeah.
Okay.
You can go ahead. Yeah.
Okay, so for the Atlas, they also analysis the W boson width. And there's one very interesting point. Their W boson mass consistent at least in 1 sigma with a similar prediction. But when they measure the W boson width, it's apart from the similar prediction, this black one, it's about 2 sigma deviation. So as I told you the story, Professor Tauhan said he only believes if this W boson mass axis be confirmed, if they also have the enhancement in the W boson width enhancement. But now we have the W boson width enhancement, but we don't have the mass enhancement here. So now things become a little bit weird. So for the Atlas, they're about 2 sigma deviation from their width, but in the mass, they have a good
Gamma W has also 2 sigma deviation.
Yeah, roughly. Here is the measurement. Here is a similar prediction. And here's about 2 sigmas. But we are not sure of the situation now. Yeah, we still need to wait for more data to confirm if they still have this kind of about almost 2 sigma deviation. Yeah, for this data point compared with this black one.
So CDF new results does not say anything about the gamma W.
No, they don't measure this value. So that's a little bit weird. Okay, so let's keep going. So another precision measurement is about the Muon G-2. And now, more than 20 years before the book happened, they have a measurement of this value about more than 3 sigma for the Snellman prediction. And here the Snellman prediction means we use a data-driven for the hadronic contributions. And in the 2021, the Fermi Lab also announced their measurements. And if we combine this book happened and Fermi Lab in the round 1 data, then we found the experimental average and the thermal prediction about 4.2 sigma. So at that time, people a little bit exciting about this Muon G-2 SS. But however, in the same years, one famous lattice group, the BNWs, they also published their lattice simulation in the Natures. And here you can see here the green lines for the lattice simulation. So before their BNCW results, people are not so take care so seriously for this lattice result because the reason you can find they have so large uncertainties. But in this BNWC20, they largely reduce their uncertainty. So now we can compare, they have the compatible uncertainty of this lattice and the R ratio with one. The R ratio means the data-driven way. So they have almost compatible uncertainties. So if we consider this lattice result, they're more or less consistent with the prediction of no new physics. So you can see in the left-hand side, if we use the data-driven way, means the R ratio, then we still have 4.2 sigma. But however, if you use the BNW simulation for the thermal contributions, then there are only 1.5 sigma, then people think this should be okay. There's no Muon G-2 axis. And in last year, 2023, we have more and more data from the Fermi lab. They're combined round 1, round 2, and round 3. And for their own data, there's about already be a 5 sigma from the thermal prediction if we use the E plus minus data-driven way. And if we also combine the two happen, it's more than 5 sigma, 5.1 sigma for the world average 2023. So that's not a whole story. So from one Russian group, they also published their E plus E minus data-driven for the data below 1 GeV. So this one you will find, although they also have a large uncertainty, but their values is even close to the experimental one. So if we combine, for example, this orange line and the blue line, the deviation between them will, of course, less than 2 sigma.
So this the last CMD3 data. That's also using the same dispersion type, relation type argument, which was used for evaluation of hadronic vacuum polarization.
Yes. But they only have a data below 1 GeV.
So it's not it's quite just E plus E minus room to hadron data.
Yes, they are data-driven. So after they release their data, people just feel confused because this one is a data-driven way, and this one is also data-driven. So they have a large difference between these two. Yeah, so that is also a puzzle. One, they have two. These two could give a very different prediction for their data-driven result. Okay, so last is a simple review of current precision measurement of some of thermal predictions and our experimental results. And let's move to the second part, the electroweak fit to the W boson mass and the Muon G-2. So let's go back to the 2 years before, when we don't know the new Atlas W boson measurement and the new Fermi lab Muon G-2 result. So at that time, let's see what can we do for this problem, the W boson mass and the Muon G-2 issues. So as I showed you before, so the first thing that we hope to do is we try to know if we have the update CDF W boson mass, then how it will change for other electroweak observables. So the right-hand side is our new fittings. And here the SS is our fitting variable minus the fitting results minus the observer one over divert the uncertainty of them. Then for these figures, of course, you can find the most pro come from this W boson mass. So that's for sure because these values is much different from the thermal prediction more than 7 sigma. And as you can see from the PDG data, they already have some deviation from the thermal prediction. Although they're smaller than 2 sigma, but they still have some deviations. And the most interesting thing is if you try to use a new data with the CDF2 W boson mass, you will find we need to have a positive pool of the top part mass and also the Z boson mass. But however, as I showed you before, now we have a very precise measurement of the Z boson mass and also the top part mass. For example, from the new CMS result, you cannot have this kind of a large pool. So means the new data from the CDF result are not support from the cinema
When you
prediction.
do this analysis on the right column, so when you evaluate the relative correction to the standard model part,
Yeah.
what is the input parameters?
The input parameter, yes.
I mean, it seems that you are not using MZ as an input parameter.
Here is the set of the input parameter we use.
Huh?
Yeah, here's the input parameter for the electroweak fittings. So we use the W boson mass, and this is an option, and also the delta alpha, the phi structure constant, the Higgs mass, leptoquark mass, strong interaction couplings, width of W, width of Z, and Z mass, and some other parameters.
But these are derived quantity, no?
This directly from the experimental results, measurement results.
Yeah, this is data. Right?
Yes, this is data.
But some of them, I think electroweak sector, if I remember correctly, is the fine structure constant at the Thomson limit, Thomson scattering, fine structure determined from constant alpha E at zero momentum transfer, and alpha S mg, and Fermi constant.
Yes.
That's your input parameter.
Yeah, we also involve them.
I'm not sure which one is input parameter and which one is prediction.
We take those values as a constant.
Hmm?
For example, the Fermi constant, we take them as a constant. And we also put them as a measurement values.
Could you show the previous slide?
Yes.
So here, all the numbers are not input.
Yeah, those values are input because we have the fit data and the measurement data. And for the measurement data means we use the, for example, we use the previous PDG's measures data. And here, the fit data means we put this measurement. For example, here we use the G-filter software. Then they will give us an output of the fit.
Okay, so all observable measure means it's data.
Yeah, measurements.
What is the O fit?
All fit means after the fitting, for example, if we put a different W boson mass, then after fitting, they will give us a smallest chi-square value. Then they will give us all fit. Then we compare the difference between the all fit and all measurement value to see if in this set is in good agreement with the model or not.
I think he's asking in your fit, which parameters do you input as fixed values?
Yes, for the input is this set.
But those are all your parameters, right?
Yeah, all right.
So then O fit minus O measure is always 0.
Fit what?
What parameters do you fit?
Yeah, parameter is this parameter. Not true.
So those are things that you fit through the G-fitter, right?
Yes.
So what do you put into G-fitter?
Yeah, this measurement we put in the G filter.
So you put in those values, and then G-fitter changes the values.
Yes. So they will tune to to the most smallest chi-square value, and they will give another output.
But it's comparing to data, right?
Yes.
So surely the same values is the most accurate, right?
Right. So, for example, if you change this input, then the output fit value will also change. So it depends on what input value we use. But for the all the items have those observables. Do I answer your question, or is it still not clear?
It's a bit confusing, but maybe I'll figure it out.
Okay. Yeah. Let's check it. Okay. So we found to be consistent with the data, they will have a large pool of top quark and Z-boson maps. But however, this is not consistent with our measurement for top quark and Z-quark. And however, this four-bell asymmetry, as we already know, there's already about 2 sigma deviation, and here the lepton asymmetry also about negative 2 sigma away from a small prediction. That's all already know, but large measurements about this one, MT and Z and delta alpha hat. And I will see more on this delta alpha hat. The reason is because for the MT and MZ, now we already have a better measurement. This delta alpha hat, this most contribution are from the non-related. Okay, so here. So we will focus on this delta alpha hat in this study. And the byproduct is we also try to update this tasking STU parameters for the new CDF result. And here, compare with the previous PDG result. And here is the one with the fit of ST and U parameters. And the second line is we make an assumption of U equal to 0, because for most of the DSM model, this U parameter is contribution very small. So if we assume this is small, then we will have a larger the T parameters contribution P. So if we consider this phi structure constant Z port, and we find there are some contributions, for example, lepton contributions, the hadronic contribution, and the top contribution. And for the lepton one and the top one, we can use the perturbation theory to calculate one by one, one order by one order. And for these hadronic contributions, we don't have this. We cannot use a perturbative way to calculate them. So we have some ways to deal with them. One is use a data-driven way. For example, we have the E plus, E minus to the hadronic data like this left-hand figures. Then we put this sigma as an input value. Then we do this principal integral. Then we can get this delta alpha hat. And here 5 means the 5 flavor schemes. And we will start this energy from the m pi 0 squared, because the lattice mass of the meson is for the pi zeros. Okay, so the final part, the final black box, we can only improve this part by the future E plus E minus collider, like the Z factory, for example, like CPC or FC, CCE. But this part is not a main concern of this work. So another thing is, let's see the thermal contribution from the Muon G-2. And here for the Muon G-2, this is a previous white papers, and you can see for the HVP, the hydron vacuum polarization, they're including the E plus, E minus, leading order, next leading order, next leading order. Most people, they only use a contribution from the leading order one, because they for NLO and NLO, they still have a large uncertainty here. And you can find a calculation for this HVP will expanding like this one. And they also depend on the sigma hat, the positions, what we get. What we get here. And here, K is the couple functions. And their integral also from the m pi 0 squared. And now let's compare with the calculation of the W boson mass and the muon G-2 in the standard models. And we find both of them also depend on how precise the measurement of the sigma hat here, the precession of sigma hat. For example, the W boson mass, it will appear in these phi structure constants. We can use these principal integrals. And for the muon G-2, for the hpp contribution, we also have a sigma hat here. So previously, when we work on this project, we are thinking, if it's possible, when we try to fine-tune this sigma alpha hat, so such that we will simultaneously solve the tension of the W boson mass and the muon G-2. So in that situation, that means we don't need the BSM contribution. But in the end, we found it's impossible. And it will be the most important result in this talk. So let's see how many ways to determine the delta alpha hat and HPP. And in general, we have three ways. The first one, as you already know, is the data-driven way from E plus E minus to the hadrons. And for this way, we can get a delta alpha hat and HPP ones. As a formula, you already know these two. So once we have the data from the sigma hat, then with a varying energy, then we can get these two values. So there's no problem. And the second one is for the lattice QCD. So you already know for lattice QCD, you can use this non-perturbative way to calculate this HBP. But however, more interesting is for this delta alpha hat, we still cannot use this one we still cannot use the lattice QCD to calculate them. So here I just write a partial. Partial means the only result from the low energy regions for the B and WC. So we will see later. Actually, when we use the lattice calculation, it's very challenging to involve the high energy part because they are using the non-perturbative way to calculate. And the third way is consider the electroweak fit. So for the electroweak fit, as we showed you before, once we have a set of the electroweak observables, then you can use this fitting to give you a predict value, the fitting values of the delta alpha hat. So there's no problem. But however, there's no way to have this HBP. So that's for sure because HBP is not relevant for the electroweak parameters. So we need to make some reasonable assumptions for the transformations of this delta alpha hat to the HBP. So this is the important things. So we need to make assumptions if we want to compare them. Okay, so here we already mentioned, here's the input values, the measurement values from the PDG, we put it. And here we consider two different sets. One is from the PDG W boson mass, another one is for the CDF 2022 NW's values. And here, let me remind you the relationship between the delta alpha hat and HBP. So as I already showed you before, so both of them are related to this sigma hat, the precession to the hadron final state in the low energy regions. So as you can see, when we compare them, so although we have different way to calculate this one, the delta alpha hat or HBP, either in the data-driven way or in the lattice QCD or the fitting. But however, one thing we know is the energy dependent of this precession. Let's figure out the G over square S. We can know this energy dependent of this value, and I will show you later why we can know this one. And for this energy dependent of this precession, we will reliably know for this energy larger than pi zeros, as we showed before. But not the overall value, the sigma hat, we don't know, and this can be adjusted. So we make these assumptions because we don't know the whole value for this sigma hat values. This is non-perturbative ones. So we make this assumption. We know the energy dependent. So we factor out this G squared root S values and times this sigma hat. This sigma hat is the value. Okay, so let me show you why we can know this energy dependent of these causations. So I'm putting in my backup slide. It's a little bit short, but small. But for example, for each final state, we can make, for example, here, the first one is pi 0 photon, pi plus, pi minus, 3 pions, 4 pions, and subset. And for this final state, we will know what is the energy range. For example, for the pi 0 and photons, we know the data taken region from 0.6 to 1.35. So in principle, we already know because of the defined final state, we already know the energy range dependence. So that's the reason why I mean we know the energy dependence for this causation. But for the exact values here, the exact values we will not know because it's non-perturbative. For the lattice QCD and data driven way can give us very different results. So that's the reason why we make these assumptions, because here the G vectors we can know from the final states and label it. But sigma hat can be some true and fixed values. So based on this one, let's see how to compare with this delta alpha hat from the data-driven and lattice QCD. So from the white paper, we already know in the 5-flavor scheme, this delta alpha hat value is about 276.1 times 10 minus 4 these values. And here the left-hand side is from the BNWC, the lattice group. Right? You can see for the lattice group, they only give us 2 data points. One is from the 0 to 1 GB squared. Another is for 1 to 10 GB squares. So they only have give us 2 data points. So that's the reason why I told you we can only have partial data because for this low energy region, we don't have any informations. So that means we can have some assumption. For example, here, if we make this assumption, that means we make the scale, the rescale to the whole energy range from the pi 0 to the infinity. So we can have this kind of projection from the pi 0 to the infinity. Here, we get from the BNWC result for this HPP value about 707.5 times 10 or minus 10. Then from these values, how can we get this delta alpha hat? We do a very simple scaling. Means this value is from this one, right? The delta alpha hat from the data-driven one. Okay, then we rescale these values from the one of what we get from the HPP of the BNWC lattice QCD, and the one from the data-driven one, 609.3.1. And finally, we get this value to A1.8 times 10 over minus 4 these values. So here we make an assumption, we make a rescale of all the range from the pi 0 to the infinity. So this is one assumption we did. But however, if you see these values, you may find, based on the lattice QCD 2 data points, if we consider the 2 kind of projection, the first one is this dashed line means from the pi 0 to the infinity rescaling. And here this what kind of this one? This more heavy line, they will show you. It seems it will be more support to this projection of only to the low energy, means from the pi 0 to 1.94 GB. So, but still, we still don't know the reason because here we only have a 2 point. If we can have a 3rd point, then we will make sure the line will go to like this one or like this one. So we still need the 3rd point to confirm this one. But here you may maybe if we have a 3rd point, then we'll be close to this low energy projection. So I will show you later if this will be the low energy projection. So what is the data change for the fitting of this one? But here let's only focus on the first one for the projection of 0 to infinity. Okay, here then I already showed you before. So we can also use the global fittings to give us distribution of mu, the HPP values. And as you can see in this table, the red block, so we don't put any delta alpha head value, and in the fitting they will give you a fit values, and you can use these fit values to compare with this W mass, and also can make a transformation to the delta alpha HPP value, delta A mu values, and here again we use a transformation from this delta alpha head to the HPP and use the simple whole range projection. The way is similar to here, but we just reverse. Here we use the known the HPP to calculate delta alpha head. Then we use the reverse way. If we know the delta alpha head, we can also calculate the HPP values. Use the scaling.
So is this Nature is your paper?
Yeah, this one.
Oh, you have a paper on Nature.
Yeah, this is sorry. The Nature communication. Nature is from the BNWC group, the lattice QCD group.
Not your paper.
Not my paper.
No, okay. So
My paper is published in Nature Communication, not in Nature paper. But yeah,
wait a minute. I think if I remember correctly, I think some years ago, Massimo Passera showed the correlation between delta R and what else? I mean, done with Marciano, Solin, and so
yeah.
so your result consistent with them, or
You mean the data in the lattice one, or you mean the lattice one?
so this
I guess you mean this paper, right? This is
they
a
compare with the equivalence.
Kipling's paper in this is published in the PRL.
So this is delta R minus delta K and T versus x-axis is what? What is the horizontal axis? Mg square? What is the horizontal axis?
Here means the range of the energy.
Hmm?
The range of the energy.
Ah,
Yeah.
Q square, range of
Q
Q square. Okay, okay, yeah.
And here is a delta alpha minus delta T values, the deviation between them.
So what is the implication of this plot?
You mean this one? Let me explain again. Here, for the lattice group, for the BNWC, they only have two data sets. One is from the 1 to 0 range, another 1 to 10 range. So only these two. So because they only have these two data points, so people try to make some assumptions. So how it will be for the future extensions.
So top plot shows that the older approach K and T out and the lattice simulate calculation basically agree with the delta R.
Yes, for the delta R, that means here is the red bulk is for the data-driven one, and for the low-end data, the delta alpha head is consistent with them. In the first two beams, means the 0 to 1 and 1 to 10. But for the later on, they don't have this data. So we are not sure for the later on if they are still consistent or not consistent. So because of that, so for this prevalent papers, they redo the analysis, they find if we consider this delta alpha minus, this is a data-driven values. They try to see the difference between them. And then it seems if we consider only these 2 points, it seems a bit more close to the scaling of this pi 0 to 1.94 GeV this lower line. And this upper line is for the scaling of a pi 0 to the infinity. But now we are not sure because here the data is here and here. If the third points are here, then things will be a little bit strange. And here, this upper line and lower line is only for the scaling, the way they scale, because we are not sure the precise measurements. So later on, I will show you for the projection of pi 0 to infinity and projection of pi 0 to the 1.95, how the data will change, the measurement will change. But here, the simple example is we use the projection from the pi 0 to the infinity. And we can rescale from this low HVP value to the delta alpha hat value. And we can similarly use this way to reverse from, if we know the delta alpha hat, then we can transfer to the mean value, use the similar, the scaling way shown here. And then these are fit results. So firstly, this red lines means red line and uncertainty bound means if we put these MW values and delta alpha hat as free parameters, and they will give us a fit between this range. And the blue bound is from the PDG W boson mass prediction and the uncertainty. And here the green line is from the CDF predictions. And here the gray dash lines for the BNWC means if we consider the BNWC, the delta alpha hat, it means we put this delta alpha hat in these values, then we will get this line, this dash line, and the purple dash line is from data driven E plus E minus, and finally this blue and green dash line means if you use the MW from the PDG and the CDF value, then we do the global electroweak global fitting. They have these two results. Then it's obvious to find if we consider to fit the MW values with the CDF 2022, then it will get a very large deviation from the delta A mu, means you have an even large the Muon G-2. However, if we move on the left-hand side, means we have a smaller deviation from the Muon G-2 axis. Now we have a large deviation from the CDF2 measurement of W boson mass. So that means we cannot fit both the CDF W boson measurements and the Muon G-2 from the Fermilab simultaneously. So that is things asking for the new physics, because previously we are thinking if it's possible, we only try to do the sigma hat, the uncertainty of the conversation in low energy. So such that we can simultaneously fit MW and A mu, but in the end we find it's impossible because these two axes will move in a two different direction. So if both of the experimental results are correct, then that's for sure we need a new physics. And here's a detail for the tables, and I can show you more clear now. So we have fit 4 different cases. The first one is indirect, means we don't put any MW values. Then our data can tell us what is a better fit value for them. And the other one is we put the PDG values of the MW values. So it's 18.379. And the third one is we consider the CDF of MW mass as an input, the 80.3335. And the final one is we use our simple combinations of 80.411 for this W boson mass. And for the delta alpha hat, we also consider 3 different situations. The first one is for the lattice one, BNWC, and the second one is for data driven E plus, E minus. And the third one is we use directly from the electroweak fitting for this delta alpha hat values, and similar for PDG and the CDF in a simple combination. And you will find our fitting results if we have, let's see here, for example, if we take the PDG as a sample, if we have the smaller fitting tension of this delta A mu means the muon G minus 2, then it will generate a larger deviation from this W boson mass measurements. And if we will have the smaller deviation from this muon G minus 2, then sorry, from the larger deviation from muon G minus 2, then it will be a little bit reduced for deviation for this NW's measurements. And most of the time for interpretation, we will have a larger uncertainty, so it will reduce the sigmas. So you can see, in principle, we cannot avoid one of it beyond the 5 sigma. So means one of them should have generate a new physics hint if both of the experimental data are correct. The similar things are for the CDF 2. You can see, for example, if we use a BMW data fittings, you will find we will have smaller tension of the muon G minus 2, and we will have a larger tension in the NW value. And here MW means the CDF minus MW. This is a fit value if the CDF result is correct. And for the data-driven E plus E minus 1, similar. If we have the smaller the tension in the NW values, then that means we will generate a larger tension in the muon G minus 2, and similar for this simple combination. And here's the visualized for this result from the indirect detection, PTG and CDF. Because of time, I will ignore these things. All the information appear in this table. So let's see the key observation for the previous table and figures. So we demonstrate that the two anomalies, means the W boson mass and the muon G minus 2, will pull the hadronic contribution in the upside directions by performing this electroweak fit. So in which the hadronic contribution was allowed to flow. If we allow this hadronic contribution, the delta had to float. Then these two anomalies were in the upside direction, so that means we need a new physics. And for example, if we if we have try to fit the better for the muon G minus 2, there will be a worsen for the tension of the CDF, the first iso for that. Okay, so now there's another issue. So I told you the data set will depend on assumption, how you do the scaling. So previously, I showed you just a very simple scaling. The third one, the whole energy range means from the m pi 0 to the infinity. So, but you also see in this lattice QCD1, so lattice QCD1, so you may wondering, it will prefer for this low energy fitting, means from the pi 0 to 1.94 GeV. So we also try to consider this low energy rescale fitting. So from the pi 0 to 1.937 GeV on this one. Of course, we can also have the fitting of the energy below the perturbative contribution from the pi 0 to 11 GeV case. But here it is not so strong modification. So we only consider the first one and the third one. So here our assumption is the part above the upper energy threshold is the same as the data driven as one uniform scaling is right. So why we need to consider this three kind of possibility? The problem is we don't know which projection should be preferred. So we consider all of them. Although the low energy projection agrees better with the PNWC result, we still need more data. So can we go beyond the uniform scaling? Because here we're scaling just the total scale. We consider linear scale. So is it possible we consider the more complicated scaling hypothesis? The questions we don't know. So maybe in the future, people can consider the more complicated scaling, then maybe they can fit data. So that's an open question here. So let's see if we change to this low energy fittings, what things will change. And this table is considered the low energy fitting. So here you can see if we consider low energy fitting, roughly speaking, it will not change a lot for this delta W mass, so almost the same for the PDG, CDF, and also the simple combination. However, for this one, it will change a lot for this HPP. As you can see, for HPP, if we change the BNW and E plus E minus fitting, it will from 3.2 sigma to 5.7 sigma. Here for the CDF one, we from 5.7 sigma to 7.7 sigma. So that means if we consider this low energy projections, then the delta bar has shrink, but the HPP will enlarge. So they have also means we need a prediction of them. We also need a new physics to explain the whole data. Okay, so I finished the most important second part. So in the final part, I will try to consider what kind of a BSM model that can explain both this W boson and Muon-2 axis. And there are many different kinds of possibility of this new physics model. Here we only consider a simple one, the scalar leptoquark models. Okay, so the model part, we consider this one, one singlet and one triplet scalar leptoquark and define this way. There is a colored triplet and SU2 singlet and triplet. And the final one is for
So you need both.
Yes, we need both. Only one is not enough to explain both of the W boson mass and Muon-2 axis. And we will see later the most important part for Lagrangian is the missing part. The missing part means the missing between this S1 and S3. And this missing is important because we hope to generate the mass difference between these two for this STU T parameters, Pascal T parameter here. And the missing is by the Higgs bosons. And the second one is for the leptoquark missing, means the S1 and S3 mixed with lepton, semi-lepton and quark, and is in the second line here. And here in the first part, we just simply assume there's no S1 and the left-hand lepton and the quark field. But I will show you later, actually this left-hand lepton and quark mixing were important for the Higgs decay to mu plus mu minus constraints. But let's see it later. So if we hope to explain this W boson mass and the Muon-2 axis, we mostly need these two Lagrangian. The mixing part means the S1 and S3 mixing, and also the S1 and S3 coupled to the lepton, semi-lepton and quark in the standard models. And simply after the electroweak symmetry breaking, we will have four scalar leptoquark. And one is with an EM charge of Q charge equal to 4/3, and 1/-2/3, and 2/1/3. And actually, in this analysis, the most important one is this two with the Q equal to 1/3. They will have a contribution to the Muon-2 and W boson axis. So strategy is one. If we can have this leptoquark, and because they will have the coupling of this in their mass eigenstate, will have both the left-hand side and the right-hand side coupling. So we will have this so-called chiral Philip enhancement. So we will have a factor of, for example, a top quark over the Muon mass. So because of enhancement, we can have a large contribution to this one loop diagrams here. So that will give us enough contribution to the Muon-2. And the second one is if we consider a mixture of this S1 and S3s, then after the mixing, we can write down the mass splitting and also these two mass, the S1 and S2 and S3 between the S plus and minus and the missing angle theta phi. And here is the split formulas. For example, for the W boson mass, then we will have this Pascal T parameters, and you can see the most important things is depend on this mass of S3 and S plus and S minus. So in the limit, if we have the M1 and M2 have the same mass, then this loop function will get 0. So we will not have this extra T parameter. So the mass splitting between these lightest two leptoquarks is important. So light leptoquark particles is important. So that can generate this non-zero T parameter. And once we have these T parameters, then this the delta MW can be written in this way. So this is a leptoquark contribution for the W boson mass on one loop. And for the Muon G-2, one loop is generated from these Feynman diagrams. And thanks to this chirality flipping enhancement, we will have this MT over MU values. And here this formula also depends on the missing element. So for this one, we depend on two factors. One is this chirality flipping enhancement. Another one is this missing values. So we put on these loop factors, then we can calculate the size of the Muon G-2 contributions. And here is our final result when we use this model to explain this Muon G-2 and the W boson mass axis. And in order to fit the CDF W boson mass and Muon G-2, if we consider this data driven, for example, E plus E minus 1, it requires the mass splitting between these two lightest leptoquark. The mass splitting is required to about 70 GeV, and coupling is about 1/7. Although it's very close to this non-perturbative region, means these lambda values in our Higgs photon. Here, this value is very close to the non-perturbative, but it's still allowed here. And if we try to use the BNW1, then of course it allows in the 2 sigma regions to 0, means we don't need this extra contribution. Okay, so it seems it's okay to use this leptoquark to explain both the MWs and the Muon G-2 axis.
Do you check the modification and of ST parameter separately?
Yes, we numerically change the contribution from S and U parameters. They are very small and can be safely removed. And there are also one very interesting thing is if we try to use the leptoquark as an explanation of W boson mass, then we find the lightest leptoquark should be less than 2 TeV. The reason is if we want to fit the data, the T parameter should be between the 0.14 to 0.17. Then we put in these simplified values and also require this lambda to be perturbative. Then it will naturally give us an upper bound of this M minus means the lightest leptoquark to be 2 TeV. So in the near future, for example, round 3 or the high velocity LC, we should know if this scenario will be confirmed or be ruled out. And also the mass splitting is is smaller than 100 GeV. So in principle, we will find 2 leptoquark around TeV. This is our strong prediction for this model. And the other one, if we try to consider the Higgs decay to mu. Actually, this already have give us a very strong constraint, this leptoquark model. So previously, we don't involve the left-hand coupling between the S1 and the left-handed quark and the leptons here. We don't make this coupling. But however, after we finish this work, we found they will get a problem from the Higgs decay to mu. And here, this the brown region is the bound from the Higgs to mu. And if our model is on with the assumption of no left-handed coupling of the lepton and quarks, then you can find to fit the values of the Muon G-2 bound, then there's no allowed values. It's already been ruled out. But however, if we only assume a small left-handed coupling of the order 10 or minus 2, then it's still allowed. So that means in order to fit all the possible data, we still need this left-handed couplings. But however, you will find once we have, in the future, once we have a very precise measurement of the Higgs to mu plus mu minus. It can also confirm or rule out. So directly search for this leptoquark or use the Higgs to mu plus mu minus will be very important measurement to check our models. Okay, so of course we know there are other models with both the W boson mass and the Muon G-2 axis. Although this model already been ruled out, it's also okay because we can try to study other models. For example, they have the 2HD and extensions, and also leptoquark models. They also have a different version. And the neutrino mass models, better like Fermi's model, and some of you maybe in this list, you can check, or some of your friends are in this list. And also there are some U1 and SU2 models, and some of them are also involve the diameter candidate. And some people also consider MNSSM and H models.
The U1 and SU2, are they dark U1 or not dark U1?
For some of them, they are considered dark U1, but for the SU2, some people have considered dark U1, and also for the SU2L.
SU2L.
Yes.
You mean adding more particle in SU2L multiple?
Yes. So for this SU2, some people consider the SU2 dark and also the SU2L. These two kind of. Okay, so that's the end for my talk. So finally, I will give a conclusion. So we show that the W mass and the Muon G-2 anomaly for the hadronic contribution in the upside direction. This is the most important conclusion for us. So that means the new CDF W mass measurement indirectly includes the deviation from Muon G-2. So these two cannot fit simultaneously well. So because that we try to consider one type of BSM model, means the singlet triplet scalar leptoquark model. So in this model, we can simultaneously explain the W mass and the Muon G-2 axis, so as well as predict the lattice leptoquark mass lower than around 2 TeV. And the mechanism for use this leptoquark because for the Muon G-2 contribution, thanks to this chirality flipping enhancement, and for the W mass, because they have some mass splitting and will cause this custodial symmetry violation. So we have a larger T parameter, about 100 GeV, and contribute to the T parameter, have a larger W boson mass enhancement. So that's all. Thank you for your attention.
Thank you for the nice talk. Any questions or comments?
So how can you test your model?
Test.
So you did not say much about how to detect this lattice leptoquark that collides.
Yes. So for example, in this model, in here, we predict the mass should be less than 2 TeV. Their charge, is about 1/3. This one. So it will mostly decay to the T mu or B mu in the final state, depending on the charge. Yeah, it will mostly, let's see, 1/3 is all the T mu, yeah, in the T mu final states.
T mu.
Yeah, T mu. So as I know,
So it couples only to Muon, not to electron or atom. So you just assume it only couples to
yes,
Muon.
for the simplified model.
For Muon G-2.
So current constraint for this Q equal to 1/3 is about 1.5 TeV, roughly these values.
Where you compare the mass shift, the W mass shift versus the coupling, can you show the figure?
Which
I'm
one?
wondering where is the standard model
This figure.
in this figure? Is the standard model shown in there?
I don't show in the stem model because stem models we just simply close, for example, close the coupling or close the mass splitting.
Because I understand PDG and BMW is consistent with standard model, right? So
No.
I would expect the standard
sorry.
model to be somewhere in there.
For the PDG, it's a little bit.
I mean,
deviation also not.
which range is this? The green region, the green region, and the BMW. I assume this is some sigma band, right?
Yeah, for sigma bond, but we don't show in these figures. But you can see, for example, for the PDG ones, if we consider at least PDG values with the let's see the PDG. I think here the bound is for in the 1 sigma.
Band is 1 sigma.
1 sigma, yes. So if we consider 2 sigma, it can extend to the values with 0 contributions.
Oh, so there is no standard model doesn't appear with
Yes,
this.
sure.
Patients.
So this part, this light leptoquark is not excluded or constrained by current LHC data.
1.5 TeV.
Oh,
yeah,
Now excluded only.
yeah, less than 1.5 TeV already. Yeah, they move out. But our conclusion is it still cannot be too heavy, just less than 2 TeV. So it can be, but in principle, if this model is correct, then it should be fine in the near future. Otherwise, yeah, it will be more soon.
So you could you show the list of the BSM models which address this issue?
Yes.
So among this, other than your model, which model do you think is attractive
Attractive.
or best, another best fit?
Another best fit. I think 2HDN is also a good choice.
Flexible.
Yes, they have some extension of the 2HDN.
In general, I mean, with soft chip breaking or not?
They also add extra particles. So except for the 2HDN, they also extra particles. For example, the singlet scalar. Or
Additional singular scalar.
Yes, it's just based on the 2HDN and for the extension.
Okay, so who are the main authors of this?
There are many. Yeah, I can share this slide with you. Yeah, I think some could also have one paper for that.
Yeah. Okay.
Yeah, I have another
Yeah, please.
question. Would you please go to the conclusion page? Yes. Just personally, I think the first conclusion looks very attractive.
Yes.
Yeah. By the way, so this is very my naive question. In order to say your conclusion is incorrect, then what should be incorrect?
That should be incorrect.
Yeah, just what I mean is now you are considering the new CDF W measurement and the Muon to deviation, right?
Yes.
Yeah. By the way, if both of two deviations are correct, yeah, correct, then your result is correct, right?
Yes.
Yeah. But what I want to know is usually whenever we observe anomaly,
Yes.
so after several years or several months, the anomaly disappears. Usually, right? Yeah. So, in order to make your conclusion, first conclusion is incorrect. Yeah. Then what should be wrong?
Okay. So if for example, if the CDF W boson mass measurement, their data, for example, if they ignore some unknown systematic uncertainty, then they will make our conclusion wrong. Or if finally we found the lattice QCD results more better than the data-driven way, then this conclusion is also not correct. But in our analysis, I also show you.
Yeah. Just
Even for
yeah.
this case, they also have some tensions. Still have some. For example, if you use the PDG's W boson mass, we still have some tensions.
then you means
Oh, sorry.
yeah.
Here because we use a CDF, but however, if you change this one to the PDG's values, then they'll be not such large, but they're still about 2 to 3 sigma deviation.
就是 since I'm not good at the data analysis, so just the reason why I ask you about this question is how much degree we can believe the experimental results about the CDF deviation and Muon to something.
Yeah, that's a good question because sometimes we don't know the detail of the experimental.
Yeah.
So we can only believe their results correct. Yes. Right.
Yeah, but just as I told you again, your first conclusion is very attractive. I think only including the first conclusion, your paper can be published in the Nature community. Yeah, very attractive.
Yeah, because of the first conclusion. The second model you can change to another model. It's okay. It's not a difficult job to build another model to explain both of the two.
Okay, let's thank to the speaker again.
Okay.
Thank you. We have a seminar dinner, so is there someone to join us? The menu I did, yeah, thank you. 1, 2, 3, Professor Ko. Five people, yeah. The menu, I determined the menu as a grilled soup, chicken, 닭갈비요. Yeah.
Did you discuss with him?
Yeah. He already agreed with me. Yeah.
So how long does it take to run Jupyter?
Very fast.
Huh?
Very fast. About 1 day.
Actually,